All right, this is the review section of this module. So let me highlight what I think, again, are sort of the critical concepts within this body of material. So first off, the free energy of a multi-component system is the sum of the chemical potentials of the different components. And chemical potentials are partial molar quantities. They are the partial molar free energy with respect to number of moles. But partial molar quantities are more general than that. Chemical potential is just one partial molar quantity. As shown here, the generic definition of a partial molar quantity is its derivative with respect to the number of moles in the system. So it's got to be an extensive quantity in order to have a partial molar quantity, but that is the general definition for such extensive quantities. When it is a pure substance, the actual value of the partial molar quantity is the value of that quantity for 1 mole of pure substance. And all such extensive thermodynamic quantities do have these partial molar equivalents. So the Gibbs-Duhem equation is a very powerful thermodynamic relationship that lets us relate chemical potentials of different substances in contact with one another as a function of composition. And it's expressed here and derived in an earlier lecture. At equilibrium, a given component has to have the same chemical potential in all phases in which it's present. If it does not, there will be flow of matter from the higher chemical potential to the lower chemical potential until things are back in equilibrium. When we have a system that has liquid and vapor phases in equilibrium, the chemical potential, here written in the 1 bar standard state, can be expressed as chemical potential in the vapor, and if it's in equilibrium, that's also the chemical potential in solution, is equal to the standard state chemical potential. So that's what it would be for the gas having 1 bar pressure, plus RT log the actual pressure of that component. Right? And so when the actual pressure is 1 bar, then of course this becomes 0, and sure enough, the chemical potential is equal to the standard state chemical potential. If it's less, this number will be below 1, and your chemical potential will go down. If it's more, it goes up. Right? And that should sort of make sense, right? As we increase the pressure on a gas, its free energy goes up. As we decrease it, it goes down. An alternative expression for the chemical potential in the mole fraction standard state is the chemical potential in solution is that for the pure liquid, and that's why I call this the mole fraction standard state, because this would be mole fraction 1, plus RT log. Now, instead of there being a 1 down here, which we didn't see in the 1 bar standard state, it really was there, but it was 1, so we just leave it out. Now it is some number in pressure units. And so we want to know the pressure relative to the pure substance pressure. For an ideal solution, Raoult's law holds, and that says that for every component, the pressure of that component, the vapor pressure, is equal to the mole fraction of that component in the solution times its pure vapor pressure, where X is the mole fraction, as I said. The chemical potential in an ideal solution, then, is just substituting this expression into this chemical potential expression, and we get what's shown here. Mixing to form an ideal solution is always favorable. It's driven entirely by the entropy. Differing compositions in liquid and vapor phases in equilibrium at a given temperature is what permits fractional distillation in ideal solutions. So the vapor above an ideal solution will be enriched in the component that has the higher pure substance vapor pressure. Non-ideal solutions are those that deviate from Raoult's law, and that can happen either negatively or positively, which is to say the vapor pressure can be less than expected or more than expected based on Raoult's law behavior. When we go to very high dilution of a component, the vapor pressure of that component, the minority component, if it's a non-ideal solution, follows Henry's law, not Raoult's law. And Henry's law says that the vapor pressure goes as the mole fraction, not times the pure substance vapor pressure, but instead times a quantity, a constant, Henry's constant. At near purity, the vapor pressure of the majority component, that's the one that's approaching purity, even in non-ideal solutions, asymptotically approaches Raoult's law behavior, and that dictates the Henry's law behavior of the other component in its minority status. In non-ideal solutions, we break down the beauty of fractional distillation in some cases, and we can have situations where azeotropes form. Azeotropes are liquids that have a composition that you can no longer separate the two by turning them into a vapor. As they boil, the vapor has the same composition as the liquid. If you have enough positive deviation from Raoult's law of behavior, you can have phase separation into two distinct liquid phases, each of different composition from the other, each in equilibrium with the vapor phase above them. Activity is defined as the ratio of observed vapor pressure divided by pure substance vapor pressure for a given component, and it takes the place of mole fraction in non-ideal solutions when one expresses, say, chemical potential. The activity coefficient tells you how different is the activity from the mole fraction. And so writing those chemical potentials then, here's the activity inserted into the chemical potential equation, and here it is just expanding activity is equal to mole fraction times activity coefficient, and so you get a sum of logarithms. In a regular solution, the excess molar free energy of mixing is entirely associated with enthalpy, and the entropy is still ideal. This is the expression one derives as a function of the activity coefficients and the mole fractions. And we looked at a theory, regular solution theory, that rationalizes that kind of activity and phase behavior, and it's based on differing intermolecular interactions between different components in liquid solution. All right. This was a challenging module. This was one of the more rich sets of content that we see in any one module. But hopefully we've had a good ride into the station. We're actually going to move on to the next module where we're still going to consider solutions, but now we're going to think about cases where we may not be able to have mixtures of all different compositions. Instead, we may be dissolving things in that only dissolve in a little bit. We call those solutes, solids into liquids perhaps, and we'll even get to salts by the end. So I look forward to talking more about that in the next module.